Hello everyone, this is Boris Lange, Manager Imaging Europe here at Advent Optics, and today it's my pleasure to talk a couple of minutes about imaging optics and taking these optics beyond the spec sheet today. So, without any further ado, we'll jump right into it. This presentation will have two parts. The first one, and this is going to be the bigger one, I'm going to talk about contrast and resolution, and then the second one are just a few quick final remarks on relative illumination and how or what kind of conflict can rise when you match that with certain sensors. But as I said, for the time being, we'll start with contrast and resolution. Let me just check. This seems to be all working okay. So let's go. So, as I said, the whole motivation of this presentation is to avoid any negative surprises when you try to match imaging optics with sensors, despite the fact that you actually took a good look in the details listed in the spec sheet. And this very first slide here demonstrates that quite drastically, in my opinion. Say that you have the choice between two different optics. Both of them are labeled with a 5 megapixel sticker. You put them on your camera, run a quick test. You put a Siemens star ray target on a backlight and just look what's going on. And with the first lens over here on the left side, everything seems to be quite all right. The blue zoomed in picture is obviously from the center of your field of view, and then the magenta one is at the 6 o'clock position, and the yellow one is in the very corner of your field of view. And again, on the left side with lens A, things look actually quite nicely. You see that the image is getting a little bit darker. We will revisit that topic in the second part when we discuss relative illumination. But if you look at the contrast over here, yes, overall the image is a little bit darker, but contrast is actually pretty good and solid still for lens A. On the right side, however, things look a bit different. On the center position, there's not a lot to criticize. Things are beautiful. On the 6 o'clock, you're starting to get to see, it's getting a little bit more washed out, but it's still acceptable, probably, maybe, depending on the application. But in the very corner, you see a very clear difference now all of a sudden. The image is a little bit brighter, admittedly, but yeah, the contrast is really just washed out in one direction versus the other. And that's why, this 5 megapixel logo or sticker on the lens is not necessarily, telling you the whole story of it. The question is, could you have avoided this by studying the datasheet in more detail? And the answer is most likely no, to be honest, because this kind of information might just be missing, or is usually actually missing on a normal datasheet. And that's kind of a problem, to be honest, at least in my humble opinion. So this is a screenshot now of the first page of an Advent spec sheet. And to be honest, on the first page, our spec sheets also don't give the answers. But that's why we have a second, third, and fourth page of specs, usually for our standard products that are available on the website. And those additional pages will answer your question most likely. For the time being, what should we do now? And it would be really nice if we had a tool where you could compare just the different levels of contrast different lenses can produce for various resolutions, for different positions on your sensors, and also in tangential and sagittal direction, which, by the way, is this picture on the right here is a beautiful demonstration of astigmatism. The resolution here in this direction is really nice. The pie-shaped, or the cones, are beautifully resolved in this direction, whereas here in that direction it's really smeared out. So that's textbook astigmatism if you care for that level of detail. Point is, you need to check whether your resolution is good in both directions. Almost I would have said X and Y, because people tend to think in X and Y coordinates if you have a sensor in mind, but for the lens itself, and as optical designers or optical people, we got rotation symmetry around the optical axis, at least in the nominal system, and that's why we always think or discuss about tangential and sagittal and not X and Y. Yeah, and as I said, it would be good if we had a tool that would give us at one glance the entire picture and tell us how good or bad a lens is for whatever application we have in mind. including the application parameters such as f-number, waveband, or working distance? And the answer is yes, that tool actually already exists, and it's called MTF curve. And well, I should probably spell it out once at least. So the modulation transfer function is exactly that. It's a plot that on the y-axis gives you the contrast, ranging between 0 and 100%. And on the x-axis, you got the resolution, which optical designers tend to put down in line pairs per millimeter. So that's an inverse spatial metric, meaning that if you have a 0 here, your objects would be infinitely separated. And as you increase resolution in line pairs per millimeter, so if you go to the right side, if you follow the x-axis here in that plot, you're bringing the details closer together, and at some point they will of course blur and will be no longer distinguishable. So that's why also we will intuitively expect that MTF curves will start in the upper left corner, and as we increase resolutions, the contrast is going to drop. That's the overall tendency that every lens will follow. Every MTF curve you will see will start in the upper left corner, and then it will drop. How fast it will drop, that's now exactly the big question, right? So, without any further ado, let's have a look at a concrete MTF curve over here. As I promised, everything is starting in the upper left corner exactly at 1, because technically or mathematically speaking, 0 line pairs corresponds to an infinite distance between two objects, and you got that. So by definition, your contrast is 100%. And now let's have a look, why are there all these different curves? So let's have a look at the legend down here. So the blue line is called 0 mm tangential and 0 mm sagittal. They happen to be on top of each other here in this plot. And this line, so the blue lines, really represent what we call the 0 mm field, which is to say this is what's happening on the optical axis or in the very center of your image. Again, optic people think in terms, our coordinate system has a 0 in the very center on the optical axis, and then we go out from that optical axis towards the corner of the image sensor. And that's exactly also what we see in the legend over here. We start at 0 mm field, then we go to 7 mm, and then we go to 8 mm field, which is to say we are now, this curve would then be representative of a 16 mm diagonal sensor, which is a 1-inch sensor format. So that's what we see here. And now we can have a very good and quick look what's going on here. Very often people draw as a rule of thumb a line at 20% and take that as a good reference, whereas as long as you're above 20%, you're safe. That would be a first way how to look at these things. And in that regard, you would have said, all right, this lens really gives you a good performance all the way up to 7 mm, because both of the green curves, the dashed and the solid ones, they are above that threshold. So the green one was 7 mm, the solid one represents tangential, the dashed one represents, again, the sagittal performance. And as you can see, there's already a lot of astigmatism going on, because that's just a huge difference between the two green lines and of course also between the two red lines. One thing to bear in mind now, if you look at this and you say, all right, this goes up to 110 line pairs per millimeter, it's not a super high resolution maybe, and if you look at the 20% line where it cuts or intersects the full field, the 8 mm curve, you're already, not even at 66 line pairs per millimeter, so that's horrible, right? That's not a good high resolution at all. But keep in mind that red curve is really just representing 4 pixels, right? 4 pixels in the corners of your sensor. And if you don't need that, if you don't need the ultimate performance all the way up to the very corner, and if you can maybe already use only an image circle diameter of 7 mm, then this lens might actually be a good choice for you. And the reason why I'm bringing it up in all that detail is, again, the motto of this presentation is going beyond the spec sheet. On spec, this performance, this 35 mm lens that I chose, is actually supposed and designed for a 2/3-inch sensor, so quite smaller. It's only 11 mm by definition. But let's say that this is really the case, and you're looking for a 35 mm lens for a 1-inch sensor, and you have a very tight budget, and you need to cut some corners. Because it's such a long focal length lens, you can consider the idea that maybe we can get away with just using a 2/3" format lens, because again, the focal length is so large, which means shallow angles within the optical design. Maybe image performance doesn't drop too fast, and in my opinion, this is exactly the case here. So again, if you can live with good performance on 7mm instead of 8, then this lens might be a very, very good option, especially if you need to have a close eye to your budget, because of course a 2/3" format lens will be significantly cheaper than a 1" lens, also probably smaller and more lightweight. So these might also be some driving factors that are into play, depending on your exact application. All right. So yeah, coming back to the original picture, don't trust on something like this is a 5-megapixel lens. Every lens has its limits, in terms of f number, in terms of waveband, in terms of working distance. And the only real way to make sure you are not negatively surprised with something like this is to have a look at the MTF curve and really use that as a tool to compare the performance of different lenses. Because the price itself doesn't necessarily tell you anything. There's going to be more expensive lenses, there's going to be cheaper lenses, but at the end of the day, what really matters is, most likely at least, the performance any particular lens brings to the table for your exact requirements. F-number, waveband, working distance, image circle. So with that, I'll wrap up that first part on MTF. So again, they are a great tool, very valuable when it comes down to comparing the performance of different lenses with each other. Could be the same lenses of one manufacturer, but it can also be the performance of any imaging lens, regardless of a manufacturer. So that's great. And that's also the reason why we print at least 2 or 3 different MTFs in each and every one of our data sheets. So you guys can have a look at what these optics do for you in more detail. Second bullet over here, I already mentioned it. I will mention it a third time because it can't be underestimated. Every lens has its comfort zone, and if you happen to have a specific application where you can really say, yes, this is the working distance I need, this is the f-number I need, this is the waveband I need, then don't feel bad, don't shy away from asking your optics manufacturer of choice to send over some MTF plots, so you can really make a very educated and good decision here. If a lens wasn't designed for the purpose you have in mind, you will pay probably too much and not get the best result out of it. So that's that. The third bullet, also quite important, please also note that MTF curves, like the one we discussed, are what we call nominal. So that means that there are no manufacturing tolerances included whatsoever. The real-world performance of a lens, or that's what we call as-built, obviously has all these tolerances, and you need to expect a drop between the MTF performance on paper in the nominal world and the as-built. So that's that. And now the last bullet, please also keep in mind, it's really just a tool to compare different lenses. It's not a tool that will tell you you will get X% contrast at any given resolution in your final application, because every single component is going to add to that overall system MTF performance, the object itself, the illumination, the sensor, the camera, the cables you use. So MTF is great, but great to compare lenses, and that's it. All right, I think we're doing pretty okay in terms of time. The second part now, to wrap things up, is a quick one. I just wanted to also spend a couple of words about the relative illumination, because there's also a chance for misunderstanding and problems down the road if you don't think about it at the very beginning. So just to bring everyone up to speed, relative illumination is the effect that, ignore all the Siemens star arrays or star patterns here. Relative illumination is really the effect that you have a certain count level on the center of your field of view, and then as you go towards the corner of your image, this is getting darker and darker and darker. So that's what we refer to as relative illumination. And you can quantify that quite easily. As I just said, you just define what's happening at 0 field. So in the center of your image, you just define that as a 100%. And then you just go from, on the x-axis, from 0 all the way up to the very corner. I picked the same example for this data here. So you go from 0 to 8 millimeters. So this curve again represents the lens performance on a 1-inch sensor. It's also the same lens, our 35mm C series lens over here. And that's the second thing you need to keep in mind if you are, to stick with the example that we discussed earlier, if you want to use a lens that's designed for 2 over 3-inch, you cannot only look at the MTF performance, you also have to check what the relative illumination does, because it might very well be that some optic or some spacer or retainer in that optical design is so small that it just entirely clips the entire light away, in which case the relative illumination curve would not be smooth. It would go all the way up until it hits that spacer, for example, then boom, it will drop down to 0, and then your corners will be flat from there on. But in this example, you can see it's actually quite nice. Yes, there is a relative illumination drop. We are dropping all the way down to 70% at 8 millimeters field, but that might be very well acceptable. Keep in mind also the MTF drops anyway, and if you only, in your application, if you can survive with 7 millimeters field, it only drops to 80, and that might be a very good solution, especially if you consider the overall cost of your system. Then performance versus cost, this important ratio, might be a very good solution for you. And also size and also weight, which seems to be also quite a big driver in, say, optics that need to go on robotics applications, drones, whatever you have. So that's relative illumination. That's how you quantify and specify it. That's also how you can look at it in a datasheet. Well, as long as the datasheet provides it. Our own datasheets, of course, do show up a relative illumination curve, but I've also seen a couple of RI plots with only one line, and that's also not the full story, one has to admit, because RI heavily depends on the F numbers. So in our opinion, as Edmund, an RI curve should also have many curves in that plot that represent the performance for different F numbers. So this is what you can see over here on the right hand side. We start at f/2 and the blue line, which, by the way, it's not the same lens now. So this is a separate piece of data, but it's good enough to show the principle. So at f/2, RI drops down all the way to 50%, but if you increase the f-stops here with each click, 2.8, 4, 5.6, and 8, you can see the RI is improving and improving and improving. So always keep this in mind. If you only happen to see a single curve in such an RI plot, it might be that the manufacturer just plotted the fastest F number, so say maybe 1.4, 1.2 even if it's a very fast lens. And yeah, if that's the case, you shouldn't be surprised that the RI curve is really taking a big hit, depending on the image circle diameter that's under discussion, the maximum field that's plotted here. But don't overestimate it. If you already know you're working at f4, f5.6, or even 2.8, then it's very well worth to reach out to your optics manufacturer and ask for an IR plot for your specific F number. So, and now the last thing I want to mention today is, even if you are okay with the performance predicted by the RI curve, there's still a potential issue lurking in the dark. And that is that this RI curve really just represents the optical design itself and nothing else. In particular, it does not include any effects that arise from a potential mismatch between the microlens array, which has a certain acceptance range regarding the chief ray angles that the optics in front of that sensor has to produce. So yeah, those of you who have been around back then, I think it was the second generation of the Sony Pregius sensors. Beautiful sensors, right? Beautiful specifications on the electronics side of things. And then you put your lens on that sensor for the first time, and A couple of people were really surprised back then because all the corners were black all of a sudden. And that's exactly what happened here. Your optic produced a chief ray angle, I think, greater than, let's say, 8-ish, just from memory, let's say 8 degrees. And the microlens array just couldn't deal with that. The microlens array is supposed to take the incoming light and bend it over to the sensitive area of the pixel. And I think it's around about 8 degrees. That's the specification. Don't quote me on that. But let's just say 8 degrees was the maximum angle that those microlenses were able to accept, and everything else was imaged somewhere else, and it was just never imaged onto the sensitive part of your pixel, so that light was lost, and that's why your corners ended up being dark. And that's really something where we as optics manufacturers also can improve a bit, because I don't think that anyone actually currently openly specifies the chief rays, the chief ray angles that any lens produces. And also on the sensor side, of course, you need to check carefully how big that maximum angle is that is accepted. So that's all about it. This last slide is just some advertising. If you enjoy this presentation, if you want to hear more from me about optics, there's an upcoming webinar from Photonics Hub. It's not free, it's 70 euros or around about 60 GBP. But yeah, that's, in my opinion, only, of course, also a nice event to hear more in detail about optics and how to interpret all the data that you can find there on the spec sheet. So that's about it. At this point, there's nothing else to say other than I thank you for your attention. And I hope you enjoyed this. And another piece of advertisement, maybe there's also going to be a panel discussion that I'm happy to be part of at some point in time during the UKIVA conference. So that's it from my end for the time being. I'll also record a second presentation on imaging optics in harsh environments. Yeah, and I think that's it. Thank you very much for listening, and see you around.